Hello my dear students, today we are in lecture number 55 of chapter 4 moving charge and magnetism. The student, today we will study the first about magnetic field of solenoid, okay, and then we will derive mathematical expression for this. So here our topic, it is solenoid. Alright, it is solenoid. First, we'll try to find out the magnetic field. We'll try to study magnetic field of solenoid. But before going to find here the magnetic field of solenoid, let us study what is solenoid. Okay, first we'll discuss what is solenoid. So my dear students, solenoid is a very simple device. Actually it is a practical device which used to obtain or to generate the magnetic field using electricity. All right, that's why it is simply called electromagnet also. The component, let me tell you the component, it consists with a hollow cylinder. This is the hollow cylinder. Okay, and this hollow cylinder must be non-conducting. All right, yes. Mainly it is made up of the porous material that you will study in chemistry, but this is the hollow cylinder. The next, we use conducting wire, very large length. This is the wire, you can say it is a conducting insulated wire. Okay, this is the conducting insulated wire. Okay, and the length of this wire is very much sufficient because we have to wind this wire over this cylindrical material. Okay, hollow cylinder. And the third thing that we use, it is a battery, this one. Okay, positive terminal and negative terminal, this is battery. So these three things we'll use to make a solenoid. Now how we'll make a solenoid? Very simple. You have to take this wire, and suppose this is cylinder, you have to just wrap the wire, that you have to wind the wire with its proper turning. Remember, the closely spaced the turning will be, it make this solenoid ideal. All right, so try to be as tightly wind, not the loosely wind, one thing. And the second thing, we have to study in our syllabus the two types of solenoid. One, it is of the finite length, and another, it is infinite length. What does it mean by the infinite length, my dear students? The infinite length solenoid, it means the length of the solenoid is so much, like it is comparatively very high with compared to the diameter of the solenoid. If diameter is very much smaller with respect to the length of the solenoid, then we will study this is as a solenoid of infinite length. Of course, we are not going to extend it to the infinity. All right, practically we use this such type of solenoid of infinite length, that is very large length. It means the length of the solenoid is very much in compare to the comparison with the diameter of the solenoid. Let we make the solenoid. Actually this solenoid we have a study in standard 10th also. So without wasting much time, let me explain you. All right, this is the porous material, that is the hollow cylinder. All right, this is the axis of solenoid, my dear student. This is called the axis of solenoid. Axis of solenoid. These are very important things. Now we are going to wind the wire. I am turning this wire. The number of turns give the magnetic field. It increase the strength of magnetic field. Okay, as you will increase the number of turning, the magnetic field will increase. But remember, if you are giving turns to the magnetic solenoid, and if the length is finished, then what will happen? If you want to increase further magnetic field, then you will give second layer turning. Okay, second layer turning. Over this turning, you can have more turning. Okay, so the second layer turning, third layer turning, in question there will be mentioned. Suppose you have given 100 turns over the solenoid. All right, and if there are two layer of 100 turns, then how much the turns will be there? So it will be the 2 times 100 turns, that is the 200 turns. Okay, now we'll connect the battery terminal across here. This is the positive and negative terminal, and the current starts flowing from here. It flow in each coil. Each turning behaves like, my dear students, each turning behaves like the current carrying coil. And I hope you remember a current carrying coil which behaves like a short bar magnet. Suppose if there are a number of coils are kept, okay, there are a number of coils are kept one another and one another, okay, besides one another, then what will be the magnetic field? The magnetic field will be increased. All right, so in this way this solenoid actually works. Now we'll discuss the pattern of magnetic field due to this solenoid. Okay, my dear students, but you should remember the solenoid practically used to produce magnetic field like capacitor used to produce electric field. I hope that you have mentioned in your notebook. Okay, let us consider for one loop, okay, or solenoid. Then we will able to understand the proper magnetic field of the solenoid. So let me erase this one. Here, suppose we took one coil, okay, one turning of the solenoid. This is the one turning. All right, this is to be turned over the solenoid. It was the solenoid. Okay, it will go again the next turning. All right, this way. Current is moving in this direction. If current is moving in this direction, what will be the direction of magnetic field? So you will find the direction of magnetic field due to this turning in this way. All right, in this direction. Okay, now try to consider one more turning. One more turning. Yes, it is one more turning. So the magnetic field B, suppose it produces magnetic field B. Okay, so the another turning will give you the another magnetic field, it is B. And what will be the net magnetic field? It will be the 2B. It means as we are increasing the number of turning, the magnetic field is also increases. Okay, now the next thing, if this is the solenoid, this is the solenoid, and we are giving the turning to the solenoid, there are a number of turns. Sorry. The conductor that we use to wind over here, this conductor is going down. All right, and at this end the conductor will out. So the let us take the direction of current, it is dot, and here the current is moving down, so the direction of current, it is cross. All right, so at each point there will be a direction of current. Remember, this is not the direction of magnetic field actually I am representing, this is the direction of current. Okay, these dots are the direction of current. Okay, my dear student, now if this is the direction of current, downward direction, then what will be the pattern of magnetic field? You can see the current is moving in this way, so the magnetic field will be in this way, that is the clockwise for each turning. There will be a clockwise magnetic field, and due to this one also there will be a clockwise. All right, there will be also a clockwise magnetic field, you can see. And for each coil, the magnetic field, it is in same direction. It means inside the solenoid, the magnetic field will add up and it will give you a magnetic field, net magnetic field in this direction. You can see over here also, if it is going down, okay, it was going down. If it is coming up, the magnetic field will be in this direction, okay, in this direction. For each turning, the magnetic field will be, if you will make a loop, you will look like this one. So you can see the magnetic field also here, it is moving in the same direction for each coil. So inside the solenoid, you will find the used magnetic field, and all the magnetic field are acting in same direction. As soon as this magnetic field lines will leave the solenoid, it diverges. All right, but inside the magnet, inside the solenoid, all the field lines are uniform, that is parallel to each other. But outside, because there is no source, okay, so there's a diverges, and inside this particular solenoid, the magnetic field remain uniform, okay, remain uniform. So this is the basically solenoid. Actually, I was thinking to explain what is the solenoid. So this was the concept of solenoid, my dear students. Now we will try to study here the magnitude of magnetic field of the solenoid. Due to solenoid, what will be the magnetic field? Okay, we are going to study. Let me wrap this one. All right. So one thing, remember my dear student, inside the solenoid, magnetic field uniform. Right now I have told you, inside the magnetic field must be uniform for very long solenoid. Okay, for solenoid of finite length, magnetic field decreases as we go towards the end of the solenoid, okay, of the finite length. For infinite it is okay, but for finite length the magnetic field decreases as we go towards the end of the solenoid, and it is maximum at the center. For practical purpose, all the solenoid it is used, and we use the magnetic field actually approx at the center. So next topic, we are going to here derive the magnetic field due to this solenoid. It is the mathematical derivation of magnetic field due to solenoid. Mathematical derivation of magnetic field due to solenoid. Okay, my dear students, we are going to find here this magnetic field due to solenoid here. Let us consider this is a solenoid. This one, and this is the axis of solenoid. We are going to discuss at the center. Suppose from the center, the total length of the solenoid, it makes here angle alpha, and this is beta. Okay, we know that there are a number of turning like this way. All right, now few other physical quantity we must remember. R is the radius, L is the length of the solenoid, okay, N is the total number of turning, number of turning of solenoid, L is the length, R is the radius, all the things have been, and I is the current. From where we got this current? Actually, the wire we used to wind up over the cylinder and we supply the current through the battery, and that current is I. Okay, one the quantity in book it is written small n. Remember, this is the number density. Okay, number density, nothing very much serious. It is the number of turns per unit length of the solenoid. Okay, my dear student, that is the number of turns in unit length. Now we are going to derive here the magnetic field due to this solenoid. Okay, suppose we take here an elementary section. We know that we don't have formula directly to use for the number of turnings, the magnetic field due to number of turns. So we are going to cut here an elementary section. Okay, this elementary section, so that it will give you this very much from this point O at distance x. Suppose this is the distance x. We cut out a small number and thickness is dx. All right, we cut at angle, certain angle, suppose theta, and this will be d theta. This will be the d theta. Okay, my dear student, what is this? Radius r. All right, yes. In this dx, what will be the number of turning? So remember, in total length L, the total number of turning is how much? It is n. So in dx length, in this dx length, the number of turns will be n by L into dx. And this is what? This is the dn. So the dn, it is n into dx. You can see n by L and into dx. This is the number of turning. Now try to recall, we have studied this particular conductor looks like a circular coil. All right, and we have studied already the magnetic field due to circular coil. My dear student, we have studied the magnetic field due to circular coil. It can be written as dB. Suppose at point O we are considering what will be the magnetic field. It is mu naught. Do you remember? Mu naught n. So n will be here dn. I, the current it is flowing, and r square, the radius is not going to be changed, divided by 2 into, if we will write here the area, then it will be the 2 pi. Okay, x square, this length, plus r square power 3 by 2. I hope you remember this one. All right, now we are going to integrate this, but we have two variables here. You can see here this dx is also the variable. Okay, it means x is also the variable, and here the number, it is going to be changed. So to solve such type of integration, we have to change first in one variable. Okay, so to change in one variable, look at here carefully. If this is x and this is r, here you can see this is x. Okay, this is x and this is r. Then you can write here tan theta is equals to x by r, and this x can be written as r tan theta. All right, we'll differentiate this x with respect to theta, then we will get, my dear student, as dx is equals to r sec square theta d theta. Okay, now we'll put the value of this x and dx in this equation. Okay, we are going to put, let me wrap this one. I can wrap this one also, all the value. I hope, my dear friends, you have made this diagram. I can wrap this one. Now, putting this value, my dear student, here dB can be written as mu naught dn, thus dn, and the dn can be written as, here we have written n times dx, n time dx, alright, I r square divided by 2 x square, x is nothing but the r tan theta, so the r square tan square theta plus r square 3 by 2. It is dx can be replaced by this r sec square theta mu naught n r sec square theta d theta. This dx is replaced I r square divided by 2 times r square is common, so 1 plus tan square theta will be sec square theta and 3 by 2. You can see, my dear student, it is 3 by 2, so the rq, and this will be the sec q theta mu naught n rq sec square theta d theta I. Alright, this r square into r become rq. It is 2 rq sec q theta. So this sec square theta will be cancel out, and this rq will be also cancel out. Finally, we have here mu naught n I. Alright, and the sec theta will be the cos theta divided by 2 cos theta and d theta, and here we have dv. Okay, we'll integrate to find the result. So mu naught ni over 2, and the integration will be cos theta will be sin theta integration. Now the very important, the limit. Try to see the diagram. Okay, rewind the video lecture and try to find out the limit. As we have written for the solenoid, all right, this was the alpha and this was the beta. Okay, and the theta started from here. So you have to take the entire solenoid. Okay, the entire solenoid. It means the angle started from here to here, but we have taken the angle in this direction. All right, so minus alpha integration, it is minus alpha to plus beta. You have to go, you have to integrate minus alpha to plus beta. Okay, now the result, mu naught ni by 2 sine beta and minus minus plus sine alpha. This is the magnetic field at O, this is at the center. Remember, this is at the center of the solenoid, my dear student. This is at the center. Alright, and for which solenoid? For finite length. This is the magnetic field of solenoid of finite length. Remember, finite length. Okay, now we discuss few cases. Okay, we discuss few cases. If we talk about the magnetic field for infinitely long, okay, if the solenoid is infinitely long, then what will be the magnetic field? If the solenoid will be infinitely long, we are having this type of solenoid. This was the angle alpha and this is the beta. This is the alpha and this is the beta. If it is infinitely long, so this angle will increase and increase, and this angle will also increase if it goes to the infinity. It means for infinity, the case for very long solenoid, what will happen? Alpha will be equals to the beta, and which is equals to the pi by 2. I hope you understand, my dear student. So we'll put this value for the infinitely long solenoid. We are going to find out the magnetic field at the center. It is mu naught ni by 2. Okay, mu naught Ni by 2 into sine pi by 2 plus sine pi by 2. Okay, here sine pi by 2, sine pi by 2, it is 1 and it is 1, 2 will be cancelled out. So finally we have result mu naught Ni. This is the magnetic field due to solenoid. Remember, magnetic field due to solenoid. Which type of solenoid? Very long solenoid, that is infinitely long. Remember students, this equation can be also written as B is equals to mu naught, N is nothing but the number of turns per unit length, okay, into I. If you will be given the number of turns, then you can use this formula. Now the next one, look at here, case 2. Okay, the case 2, at one end of solenoid, at one end of solenoid. Okay, if you wish to find the magnetic field at one end, of course this was the angle alpha and beta, but if you wish to find out at one end, so this theta will decrease and it will be 0, and the one end, if it goes to the infinity, then alpha it will be 0 and beta will be pi by 2. For long solenoid, for very long solenoid, the magnetic field at any end will be B is equals to mu naught Ni by 2 sine 0 plus sine pi by 2, and it is mu naught Ni by 2. Okay, so you can see the magnetic field at end is decreased by half. This evening I told the magnetic field as we go towards the end of the solenoid, it decreases. Okay, my dear student, and if you will plot the graph of magnetic field for the solenoid, you will see if the magnetic field at the center is this one, so as you are going towards the end, the magnetic field will be decreased and it will be the half. Okay, if this is the magnetic field B, so this will be the B by 2 at the end. Okay, so this is the graph of magnetic field versus length of the solenoid. This is not very tough to understand, my dear student. Now the next thing, here we go to do a practice for very simple numerical. Remember, I'm not going to practice over the simplest question. Of course the simple, but not the simplest. Okay, the directly if I'll give you the value of current, radius, Ni, and to find the magnetic field, that will be very easy for you. Okay, so one question, and I hope this question is it has been given in NCERT also. Okay, so this is example. You're having a solenoid here. This is the axis of solenoid. All right, the length of the solenoid is given L. All right, and the number of turning of the wire, it is given as N. The radius of the solenoid, suppose it is R. Okay, now the question, the number of turning, it is given in this wire. Suppose the current, it is I, or I have to ask actually this current only. A very small conductor, it is placed inside the solenoid. A current carrying conductor, it is placed inside the solenoid, and it is placed like this one. All right, by any means, if this conductor is applied by a current I, okay, suppose I is given, so this current is given I. Remember, this is at 90 degree, like this way. If this is the solenoid, okay, this is the horizontal solenoid in this way. Okay, and you have to place the conductor inside the solenoid, because the solenoid is very small, so you have to place this conductor, if this is the conductor, then in this way. Okay, you have to place in this way. That is, this conductor and the axis of solenoid both are in the same plane and it is in horizontal plane. Okay, this is the question. With the help of the battery of the string of the conductor, the current is established I. Now the question, if this conductor having the mass m and inside the solenoid, if this conductor will lift, of course it will fall down inside the conductor, but the question is being asked, what should be the current maintained here, suppose I dash, what should be the value of current through this winding so that this conductor does not fall inside the solenoid? This is the question, my dear student. Okay, how will solve? So look at here, I am solving this one. Remember, if this conductor is not falling down, it means its weight is balanced by this weight mg. It is balanced by some force and opposite force. All right, and that opposite force is nothing but the force on current carrying conductor. If any conductor is placed inside magnetic field and it experiences a force, all right, and it is nothing but the I love sine theta. We have studied here the ILB, the maximum force at will be for the 90 degree, so the sine 90 will be 1. Okay, ILB. Now the very important thing, B, magnetic field. Who will give magnetic field to this conductor? Of course, the magnetic field will be given by the solenoid. It means you have to use the magnetic field of solenoid over here. So the B will be nothing but mu naught Ni, and the value of small n converted into the capital N by L, because we are having here the L and N, not the small n. All right, mu naught Ni, and current I of this solenoid. All right, I dash. So you can see this mg is equals to I. This is the current flowing through this conductor which is placed inside the solenoid. L, length of the conductor, and B, behalf of B you can put N by L I dash. Now you have to find this I dash. All the values are given, my dear students. I hope now you can solve this one. So thus I dash will be very simple. Thus I dash will be mg. Okay, I dash will be mg divided by, or the mgl divided by mu naught nil, mu naught ni small n. This is the current. Okay, there are a number of questions, my dear students, I have given in my assignment. Okay, and you should start solving the question using that assignment. You will get practice more and more, my dear student. Okay, my dear student, here we have studied the solenoid, the magnetic field of solenoid, but we have used here the complex calculation for finding the magnetic field of solenoid. In next lecture we will start Ampere circuital law, and you will see that Ampere circuital law make this all calculation in 3 to 4 lines, and in examination you will be asked to find the magnetic field using Ampere circuital law. But this was also very important because few year this was asked to find the magnetic field of solenoid having the finite length, because Ampere circuital law will give you the magnetic field of solenoid of infinite length. That is the limitation of Ampere circuital law. We will discuss in very detail. Okay, and that Ampere circuital law we will start in next lecture, my dear student. Okay, the one thing that I repeatedly request you all, my dear student, try to see my videos very carefully, and if you will find any mistakes, kindly leave the correct thing, or at least let me know in the comment section so that I can rectify. Okay, my dear students, so this is all about the today's lecture, my dear students. Thank you very much.